Imagine this scenario. You have a perfectly healthy system, and one of your microservices is responsible for handling orders, the order service. Sales are flowing, everything is running smoothly, and then, without any warning, the entire system goes down. You try opening the products page, it won't load. You check the profile page, it doesn't respond. Your server starts throwing 500 for gateway timeout errors at everyone. You rush to inspect the logs, only to discover something surprising. The order service is completely healthy. Its database is healthy too. The real problem is that the payment service, or the demand service, is either extremely slow or completely down. So here's the question. If the demand service is the one that's failing, why did the order service fail with it? Why did the failure spread through the entire system like a line of falling dominoes? Welcome to another system design capsule. I'm Mustafa Solomon, and today we're talking about the nightmare that wakes every head of engineering and software architect in the middle of the night. Cascading failure. To understand this disaster, we first need to understand how our server works. If you're using Spring Boot with Tomcat running on its default configuration, you're using a model called thread_request. What does that mean? Tomcat maintains a pool of worker threads called a thread pool. By default, it contains 200 threads. Every time a user places an order, the server assigns one thread from that pool to process the request. Now let's walk through what happens during synchronous communication, step by step. A user named Ahmed places an order. The server assigns thread 1 to handle his request. Thread 1 executes the code until it reaches a synchronous HTTP call to the demand service to retrieve some data. Unfortunately, the demand service is hanging and taking an extremely long time to respond. At this point, thread 1 becomes blocked. It's sitting there in memory doing absolutely nothing except waiting for a response. Now, within the same second, 10 more users arrive. Then 50. Then 100. The server keeps assigning more threads from the thread pool, and every one of them ends up waiting for the exact same unresponsive demand service. Within just a few seconds, your entire thread pool is exhausted. This is known as thread starvation. And that's when the real disaster begins. A completely different user, let's call him Mohammed, visits your application just to browse the product catalog. His request has absolutely nothing to do with payments or the demand service. His request reaches the server. The server attempts to allocate a thread from the thread pool and discovers that there isn't a single thread available. Now incoming requests begin piling up in the request queue. Once that queue becomes full, typically around 100 pending requests, the server starts rejecting new connections and returning errors like connection refused or 500 for gateway timeout. At this point, your server is effectively dead. Not because your code is poorly written, but because your application kept waiting endlessly for another service with no limits and no protection. If your business requirements force you to use synchronous communication, how do you protect your server and prevent cascading failure? There are 4 essential protection mechanisms that should be part of every production system. Strict timeouts. Circuit breaker. Bulkhead pattern. Rate limiter. 1. Strict timeouts. One of the biggest engineering mistakes is leaving your timeout settings at their default values, which can be as long as 30 seconds. Instead, enforce a strict and short timeout, say 500 milliseconds. If the demand service doesn't respond within that time, terminate the request immediately. Throw an exception, release the thread, and return it to the thread pool so it can start serving other users. 2. Circuit breaker. This is the smart guardian of your application. It sits inside your code before any network call is made. The circuit breaker continuously monitors requests. For example, if it notices that 50% of the last 20 requests have timed out, it realizes that the downstream service is failing. It immediately opens the circuit. Once the circuit is open, your application stops sending requests to that unhealthy service altogether. Instead of wasting threads waiting for responses that will never come, it fails fast and immediately executes a fallback response. 3. Bulkhead pattern. This pattern is inspired by ship design. Ships are divided into isolated compartments so that if one compartment floods, the entire ship doesn't sink. We apply the exact same idea to our thread pool. Instead of allowing all 200 threads to serve every request, we reserve a small dedicated pool, say 10 threads, exclusively for calls to the demand service. Now, even if that service becomes completely unavailable, only those 10 threads are affected. The remaining 190 threads continue serving the rest of your application without interruption. 4. Rate limiter. Finally, we place a rate limiter in front of the request queue. Think of it as a security guard standing at the entrance. It limits how many requests are allowed per second, protecting your server from sudden traffic spikes that could overwhelm the queue and bring the entire system down before requests even reach your application. To implement all of this in a real Java and Spring Boot application, there's no need to reinvent the wheel. Don't reinvent the wheel. The industry standard today is a library called Resilience4j. It provides clean and easy-to-use annotations that you can simply place on the methods responsible for communicating with external services, such as @circuitbreaker, @bulkhead. Inside your application.yml file, you can configure everything you need, including the bulkhead thread pool size, the circuit breaker's failure threshold, timeout durations. Using a fallback function, you can return a graceful response to your users instead of letting the entire system fail. For example, you can serve cache data or simply inform the user that their order is being processed while the system continues running normally. Here's today's engineering takeaway. In the world of microservices, failure isn't a possibility. It's inevitable. That's why we design for failure. Whenever synchronous communication is unavoidable, protect your system with strict timeouts and circuit breakers. Never let your server go down simply because another service is having a bad day. That wraps up today's system design capsule. If you enjoyed this episode, don't forget to like and share it. And let me know in the comments. Have you ever experienced a cascading failure in production? If so, how did your team handle it? If this capsule helped organize your thinking, subscribe to the channel so you never miss the next one. See you in the next capsule. Thanks for watching.